Hello, my name is Alla Rozovskaya. I will present our work toward robust evaluation for multilingual grammatical error correction. Can large language models replace human references? Grammatical error correction is the task of the automatic correction of errors in text. In the last few years, large language models demonstrated impressive performance on many natural language tasks, eliminating the reliance on supervised data. However, experiments on grammatical error correction yielded mixed results. On the one hand, studies on English suggest that LLMs propose high-quality corrections. On the other hand, standard evaluations indicate that LLMs lag behind supervised GEC models, especially on languages other than English. However, we hypothesize that LLM performance may be far better than reported due to the weaknesses of standard evaluation metrics. Therefore, in this work, we aim to develop robust evaluation approaches for grammatical error correction across languages. The goals of our work are twofold. First, we aim to develop automated evaluation that has interpretable metrics. Our second goal is to assess LLM prompting quality and compare it with supervised SOTA models across languages. Grammatical error correction is a text generation task, and similarly to other text generation tasks such as summarization or machine translation, we have what we call the multiple gold problem, where given an erroneous sentence, there are usually multiple ways to correct mistakes in it. This impacts evaluation of the GEC systems. Standard reference-based evaluation proceeds as follows. Given an input sentence that may have mistakes, a human expert corrects the sentence to generate a fixed reference gold, or RG. The input and the RG are aligned to produce gold edits. Similarly, the input is aligned with the system hypothesis to produce system edits. And correct edits is the intersection of gold and system edits. We can then evaluate performance in the standard way using precision recall and F-score. A well-known problem with reference-based evaluation is that the space of possible corrections is typically large. However, GEC models are evaluated against a small set of human-generated references. As a result, reference-based evaluation severely underestimates system performance. The problem is exacerbated in languages other than English, since benchmarks in other languages typically contain one gold reference per input sentence. In our earlier work, we proposed to evaluate GEC models using what we call closest gold references. We define a closest gold reference as a reference text that is as close as possible to system output in the space of all possible corrections. How can we create closest gold references? In our earlier work, we proposed to create them by manually correcting the system output itself instead of correcting the input text. Such a reference, on the one hand, directly quantifies the remaining errors in system output, and on the other hand, incorporates all valid edits proposed by the system. We claim that evaluation against CGs provides a more realistic assessment of system performance compared to using standard fixed references. See paper for detail. Let's compare a fixed reference and the closest gold reference. In the top segment, we see an input sentence and a fixed reference RG that is created by directly correcting the input sentence. In the bottom part, we see a CG reference, which is created by correcting the system output itself. When we evaluate with RGs versus CGs, we typically get a higher score when a system is evaluated against a CG. The reason for the higher score is that the CG reference avoids penalizing legitimate edits, yet reflects the remaining edits that the system had missed. One problem with human CGs is that creating human CGs is costly, since it requires creating new references for each system output. In this work, we propose to automate the CG evaluation methodology by making use of an LLM to generate the CGs. We show that this can be done reliably in multiple languages. Crucially, the proposed method retains the interpretability of reference-based metrics, precision recall, and F-score. We use LLM CGs to compare the performance of supervised models and GPT-4 on 14 GAG benchmarks across 12 languages. We show that under closest gold evaluation, GPT-4 exhibits stronger performance on the majority of benchmarks, with several exceptions on low-resource languages. We use 14 GAG benchmarks spanning 12 different languages. For each language, we compare performance of a supervised state-of-the-art model, SOTA, and GPT-4 via zero-shot prompting. We first compare GPT-4 and SOTA using fixed references. We find that SOTA outperforms GPT-4 on almost all benchmarks, confirming earlier results. Next, we generate human CGs for 4 benchmarks in English, Russian, and Arabic. Evaluation with human CGs reverses the results of evaluations with fixed references on all 4 benchmarks, demonstrating that GPT-4 outperforms SOTA models. Next, we generate CGs using 2 LLMs, Claude and Llama. We find that Claude and Llama CGs agree with human CGs in all rankings. We also find that Claude and Llama CGs show high correlations with human CGs. By contrast, standard references show no correlations with human CGs. Finally, we compare GPT-4 and SOTA performance on all 14 benchmarks using Claude and Llama CGs. We find that Claude and Llama provide the same rankings for SOTA and GPT-4 on 9 out of 14 benchmarks. Disagreements occur mainly on low-resource languages when longer contexts are required. We find that Claude seems to be more robust than Llama on low-resource languages. To conclude, the key findings and contributions for multilingual GEC evaluation: we propose to automate this CG evaluation methodology. We show that high-performing LLM CGs can be used to replace human references for many high, mid, and low-resource languages. Then we compare GPT-4 and SOTA using LLM CGs. We find that GPT-4 outperforms supervised SOTA on most language benchmarks, reversing results with standard reference-based evaluations. Thank you.